All right. Hello, everyone. Hope everybody's having a good morning today. For the first minute or so, I'm just going to let these slides play. And as we wait for everyone to trickle in, we'll get started in just a couple of minutes. So while we wait, it'd be great to know where you're from. So if you're watching right now, we'd love to hear what city you're calling in from. Good morning from Seattle. That's awesome. Always love to see you on, Rob. Lisa from Wesley Chapel, Florida. That's fun. I don't think we get a lot of people from Florida. San Jose, also fun. I think Justin, I've seen you on here a couple times as well. Always good to see you again. All right, so we've kind of let these slides loop for a couple minutes. I think a lot of people who are going to be joining us from the beginning are here. So I'm going to take these slides off the screen, and Vishaka and I will come on screen. So today we've got a great session from Aperture Data with Vishaka Gupta. So I will let you introduce yourself, Vishaka, and then talk to us a little bit about Aperture.
Hi, Eugene. Nice to see you again. Thank you, everyone, for being here. I'm Vishaka Gupta. I'm co-founder and CEO of Aperture Data. Prior to starting Aperture Data, I was at Intel Labs for over 7 years, which is where we kind of started working on what I would be talking about. I'll talk about today. Been computer science background through and through, and it's been interesting to see all the things that have been changing so rapidly in the space of multimodal AI and to be part of it.
Yeah. So last week we had Jason from Neo4j come talk to us about GraphRag. And I think before we kind of get into, I know you have some material ready for us to show a demo and things like that. Before we kind of get into this, I'd love to know a little bit about, I think it would be great for you to tell us a little bit about Aperture and how it's unique from some of the other vector database or AI database type offerings.
Also, not to steal thunder from my own rest of the presentation, I would say, when we got started, it was it was a few years ago back at Intel. We were targeting essentially applications where you would be dealing with a lot of unstructured data. So at the time, we were focusing on images and videos, and the goal was how do you redefine cloud systems architecture when you're going to be dealing with that type of data, but not for streaming, but for machine learning sort of use cases. So you would be dealing with a lot of, go back and access the data, search for the data, improve metadata, deal with annotations, deal with embeddings. So when we started building this, our perspective was more around, well, data scientists and data engineers, they already have to spend a lot of time understanding the data. Right? They have to be able to use it. They have to be able to enhance it and all that. Why should they have to spend time assembling pieces of different data tools in order to get there? As we started looking around, the only option was, well, the videos go in cloud buckets. And now I have like a spaghetti slide in my presentation where I show this exactly like step by step. And it's funny how much it resonates with everyone because you start with dumping data in buckets. That's like the very first thing. You bring in some database to put the metadata. Then you gradually realize, well, you got to search and pull, and then you got to insert annotations. And then after that is when you get into vector search or search by labels and things like that. So it just takes a very long time before you can even get started. So, when we built it, we were like, why can't we simplify this? What if there was a database that was built with the understanding of the complexities of all this type of, different data modalities that you would deal with, but the interfaces were built so that it was easy to work with the entire machine learning pipeline. So we didn't necessarily start particularly from like, oh, vector databases are suddenly going to become like the thing that everyone talks about. But we realized that that was a very important way to find the data you're looking for. So that's kind of how, like, so we built it in. But what also happened was, because we were building it from like how many different ways can you find the data, and how many different formats would you need the data in. So we ended up building like a way to search by metadata or annotations, which is why we actually have a graph database behind ApertureDB interface. And together, that helps us combine the graph, vector, and label searches, and then also let you access the data. And that is where the distinction comes in, because we weren't just built for just purely supporting vector search. It was basically search for this type of data. We just happened, like, we ended up defining the interface to support all these different sort of ways of accessing the data.
Yeah. Yeah, I mean, I think it's really unique to kind of have the graph and vector stuff in one. So I'm going to bring up your slides and let you start off your presentation. So let's do that. Here we go.
All right, thank you so much. And please feel free to ask questions in between. I know I've seen some of your sessions earlier. It's always good to have like an interactive. So anytime you want to ask questions, just stop me. I've just prepared some quick overview here. And I want to show you a few examples of what this looks like, and then we can come back to Q&A. So let's talk now, as we already started, about choosing the right data tools to build for multimodal AI, which I think it's a fair assumption, if you guys are here, that that's top of mind for you. Now, since the audience might be a mix of experts and people getting started, I just put in like a few terms, and then I'll go into the details of Aperture and a few demos, and then we'll discuss whatever questions you have in mind. So as you might already know, the simplest example here on multimodal AI is just autonomous cars combining various signals or data to generate commands to drive like humans. Which is like the biggest goal. It's like you want, the AI needs to, it's trying to behave more and more like humans, and we process a lot of different types of data on a day-to-day basis. So that's really what we're trying to achieve here. Which brings us to multimodal data. And we've seen multimodal data very often in the context of healthcare. And the reason I'm using all these application examples is I always found it was easier to kind of put it in context of all the things we've seen in terms of use cases, which is when the data starts to make a lot more sense. Like, doctors will refer to their previous notes, blood tests, X-rays, CT scans to diagnose patients. Just one type of data here, just like their notes, especially if you look at how squiggly their notes can be from some doctors, they're not sufficient in painting the whole picture. It's applicable to a lot of other contexts. Like, let's say I was monitoring a casino. You might think that someone is just observing the game, but they might be focusing and listening in on someone counting cards for them. So now what do we usually do? So you've collected all this data in any application, any vertical that you might work in. You'll have collected at least a few modalities of data. If nothing, there is log data. There is description of who created the logs. So there is some metadata. And then there might be some PDF files. There might be some snapshots that you take. For any vertical, you'll collect a few different modalities of data. And what we essentially want to do with it is search it and find something we need, or draw some conclusion. Or if you work in machine learning specifically, you might want to train some models for them to start automatically detecting things. Now, until we were dealing with numbers, it was easy to look for a number in a set of numbers. Well, relatively easy, but really hard to automate looking for images or videos or such complex unstructured data. You might argue, why don't we just use some captions or label to find what we need? But it's not always straightforward or consistent to get labeled data at scale. Now, which is what brings us to embeddings. An embedding, a feature vector or descriptor, all names that I'll be using interchangeably here, It's just basically often a lower dimensional representation or signature of the data it represents. And it typically is a series of numbers that you might extract from your machine learning model. There is a lot of ways in which you can get to embeddings. Today, we can mainly just rely on existing models to give you the embeddings you need, or train your models and then use some logic to extract them. And because of the way they are extracted, embeddings of items that are similar tend to gather close together or cluster close together. So now what do? We basically can use them to find similar text, similar images, similar videos, similar audio clips, even when we don't have keywords attached to them. Now that sounds very useful. So of course, in order to find these items we are looking for, we need vector databases for vector indexing, similarity search, and classification. Now there are a lot of choices in the market, especially since last year. I think there is an index on Superlinked which lists about 40 vector databases at this time. And I didn't capture all of them, just some of the major ones we hear names of. Now, while these vector databases can solve vector indexing and search very well, the overall data problems get messy very quickly. And let me give you some examples of what I mean there. So it's a common example, chat support. Someone wants to find what error XYZ means for their machinery. But they also want, they want to find what that error means, but they only want responses from, the machinery that was built between 22 and 23. And there is some requirement on the manuals from which you pull this information should be written by some specific team. And also, while they're doing this, they also want the manual. So it's no longer just a vector search that will return relevant samples that an LLM can then create answer from. You want the response augmented with complex metadata filters to make it relevant to your task. And then you want to actually follow it up by accessing the PDF itself. So that's one example. Now let's take a more traditional use case of multimodal AI. We work with a visual AI team at a big box retailer. And their main use case, and something that we've seen across e-commerce vendors is recommending products to their customers. And ideally, they want to do it by visual features because that's how we purchase things. We purchase things based on colors, textures, shapes, not necessarily just by brands and well, of course, pricing plays an important part, but the visual feature is what captures our attention. But they want to return those images from the fall 2023 catalog. You could indicate year and season in the embeddings when you're doing a vector search somehow, or you could enhance that search with metadata stored differently. So that's one aspect of where you could constrain by metadata. But even beyond that, before they could get to the point of recommending or vector search and metadata constraint, these guys had to do a lot of things, right? They basically had, given the task is so specific, to use their catalog off-the-shelf models might be a good start for them, but not give the desired results. So their overall tasks, even before they got to the vector search, would be, transforming and basically cataloging their data, accessing it correctly to train their models, using the models to extract embeddings and other metadata information, and then finally they can do the vector searches. The reason I want to give you these examples is that's where we basically see when we go beyond the use cases that are very popular today in production deployment, or when you want to use them for businesses, the requirements that we come across is certainly index and search high dimensional embeddings and from any multimodal data type. But you also want to allow metadata filters. And very often you need to actually retrieve the original data, which may not be just simple text. It might be images or videos or PDFs or any of those other data types. In fact, if you go, if you really go deep and you want to think about what you are going to need to deploy in production, you're going to need high throughput vector search and classification. You're going to have to filter on rich and evolving metadata. Remember that the metadata keeps changing all the time. You want to be able to connect to original data, as we saw. You need reliability and stability at scale because this data grows really fast. And of course, there are enterprise features. You want to be ready for that, be cloud agnostic, and very often be able to deploy in customers' VPCs because of the sensitive nature of data. So now it brings me back to what were we missing in the vector database part? The vector databases miss complex schemas, don't often deal with the data itself. They're not very often built to work with the rest of the AI pipeline. As you saw there in that the retailer use case, there were a lot of other steps that went before from the training and labeling and all those aspects. And of course, you still have to figure out, there is a lot of choices in terms of, is it cloud hosted, is it scalable, does it support all the enterprise features we need? And when you put all those things together, what we've seen across our customers, whether they're dealing with emerging Gen AI use cases or traditional machine learning use cases, between prototyping and production, when all their data needs to be incorporated to do something useful, we see this sort of a spaghetti mess evolve in their data types. So, you start with receiving different types of data, like images, metadata, maybe transcripts from audios. Naturally, you put them in cloud buckets, as we were talking earlier. You might take the data, the metadata, put it in some form of databases. If you are going to need label data, then you query the data, send it to labelers, take the labeling formats back, and you have to land them somewhere. And then everyone in the team essentially ends up writing their own scripts to query information from the different pieces, depending on what they need. In fact, when we are talking about computer vision data, very often, you might even have to deal with some very finicky libraries like FFmpeg or OpenCV. And then finally, if you are building systems of recommendation, you are enabling LLM or RAG searches, that's when you need the vector search or vector databases. So, we were choosing the tools that are known for that specific data type, but what we landed with is this complex glued together system that's very often very long to install. You have to enable translations among all these pieces. And imagine if you had to debug in any of this. It becomes quite messy, quite fast. And it's not really scalable to different use cases and amount of data. And so that brings me to what did we do about it? Our solution is a database that not only understands the complexity of multimodal data management, but also understands AI requirements to make it easy for teams to adopt and deploy in production. So that's what ApertureDB is. It natively supports management of multimodal data. And we did start with the focus on computer vision data. So you will notice if you go to our API page that our support for images and videos is a lot more advanced. You can do, in fact, you can say, find me all the images from 2 days ago and give them to me in thumbnail format. So you'll be able to do that resizing and rotating or any other form of pre-processing right through our query interface. And we'll do it server side, and you'll get the data in the format that you want. And that brings me to a really key piece of this. The metadata is really important. So we manage application metadata as a knowledge graph, where basically everything, including application information, any images, videos, blobs, anything you might add in the system, has a representation in the graph and is connected to each other to help you visualize, to help you represent semantic relationships on them. And annotations, same way, are part of this metadata. And the graph database that we built is memory optimized to help scalable operations. Then, as we were discussing earlier, an important piece of this is to be able to find by similarity. So we also have a way to index feature vectors and then find visually or find similar objects by vector similarity. Now, one of the big things we realized was if we really want to make things simple for users, they shouldn't have to know that there are all these components behind the scene. So one of the things we added, and one of the key features, is this query engine, or that helps us provide this unified API to deal with all these multimodal data types. Basically, with something like this, ApertureDB offers, it offers unified API to store, search, and access all of users, images, videos, any other block types, metadata, annotations, and embeddings. And it can address fundamental expectations from the data layer for AI. I don't know if there are any questions. I want to make sure I pause a little bit in case.
I had a question, actually. When you're saying that we could like call Aperture to get the multimodal data back in different forms, does that mean you have like the different embedding models or the models you use to create the embeddings inside of Aperture? Or is that like something that kind of sits separately that you can kind of swap out, but is still on server side? Like, how does that work?
Yeah, so we actually consciously chose not to put embedding models inside Aperture DB. It's outside.
Okay.
So that's a great question, because what we realized, especially early on as we started interacting with customers, a lot of people wanted their own models. The extraction of feature vectors was their core IP. And now with off-the-shelf models, it's become like, a lot of the time people start with that. So what we have instead done is when you're loading data, our ETL, or like the data loaders that we offer, they have very easy ways to specify that as you are uploading this image or video or any other data type, run this model, which very often is like off-the-shelf model. So I have an example with clip embeddings, for example. And what our loader tool will do is, as it is ingesting the data into Aperture DB, it'll also run the models that you specify. And this could be for generating embeddings, or it could be for some other classification on the fly, and then just input that data into Aperture. So the processing happens outside, but we have our client-side SDK provides encapsulated functionality to run the model.
Okay, cool. And then I also had another question, which was like, when you see people use Aperture, do people like with video data and image data, you have let's say different embeddings. Do people try to use these together, or do you typically see people who are working with video data just be using video data, and people who are using image data like using image data? Or maybe do the people who are using video data try to like break their videos into images and audio? Like, how do you see people like working with that?
Yeah, so we've seen like a range. So people working with images typically end up doing images, and they'll generate embeddings from images. They might combine like with now that you have options, you can combine the text and image onto the same space and search with text. But with videos, in fact, I think just this morning we were having a conversation around the user storing videos, but also keyframes. So frames that have something interesting were extracted and stored separately, which is basically storing images. And those frames are then linked to the original video. And then we also see people, when they are working with videos, indicate what's the interesting part of the video. So on our documentation, we have an example where you can say, okay, from frame 25 to 150, or you can say from 5 seconds to 10 seconds onward, we have some event. Like in retail case, it can be someone is picking up a product. And then people still just want to extract that interesting part from the video. So that can be like either they want to extract just a frame, or they might want to extract like a clip out of the video. So we've seen those sort of usages when it comes to images, videos.
How can you compare? Can you compare images with videos? Because like, as far as I understand, you can only compare embeddings at the same length, right? So
yes.
Can you store embeddings of different length in the same, I don't know, like instance?
So in Aperture DB, if you look at our API, we have this notion of descriptor set and descriptors, which is essentially like, I think in Milvus, there's like collection and then vectors that go in the collection. So the descriptor set essentially is the search space. And there we do have this requirement that all the embeddings that go into that search space are of the same dimension. And they make sense, like, the distance metric and all that stuff that you use to find similar objects. It makes sense if you're extracting them with the same method. Because if you're extracting them at different methods, they mean different things. And you're not like, there's not going to be a correspondence as you expect it to. So what within Aperture DB, you can have multiple descriptor sets. So you can very easily have a descriptor set, which is all embeddings extracted from the videos. And then another descriptor set, which is embeddings extracted from the frames in those videos. And what you could do is, let's say I want to find frames that are similar, but then trace them back to the video, because that's when the graph comes in.
Okay, so you can link, you can use the graph to link different types of embeddings, basically.
Exactly.
Oh, that's really
the search space. So the KNN, or like the near neighbor search that you would do, that would be in the you know, like all videos embeddings together, all image embeddings together from the same extraction method and dimension. But beyond that, they are connected in the graph that we build, which is why like having that notion of the integrated graph is really powerful when you start doing these things.
Oh, okay. So we have a question from the audience as well. Is the knowledge graph created automatically, or do you have to manually do it?
So at the moment for us, we do expect the users to input that information. I know there's like, I've been reading on, you know, LLMs being used to extract the entity and relationship information that you can then put in Aperture DB. But we do rely, because the meaning of, and you know, I can show you a graph example, the meaning changes with application. And being a database layer, we support different applications. So you need to be able to, like, you know, that's why that logic, or what the nodes in the graph represent and what's the relationship, that's very tied to the application. So we leave it to the application layer.
Okay, very cool. There doesn't seem to be any other current questions from the audience. Are you going to cover the different types of distance metrics and stuff like that in the next slide?
Yeah.
Okay, cool. Yeah, that's better right now. Okay, cool. I'll let you keep going then.
Cool. No problem. But so a very quick, this is more like an ecosystem. You know, how do you think about Aperture DB in the rest of the things you're doing? So as we saw, Aperture DB can manage the data and metadata. It can store and access this from the data from cloud buckets or storage that Aperture DB manages, and we run in any of your cloud providers. We also have a good set of additional tools, and this is what is really like the key in terms of, you know, once you set up the server, you shouldn't have to think that there is some, you know, database or something running. You essentially deal with our, most of the times, Python SDK, which you can pip install. We have data loaders, so we make it really easy. You specify comma separated value files of any type of data, and the loaders will just do parallel ingestion and apply the transformation like we were talking about earlier. If you specify that, you have the vector search and classification, or the metadata search and queries that you can do. In fact, you can, you know, use Aperture through frameworks like LangChain. Then there is we also, so, you know, I think, Eugene, you asked me earlier, like the differentiation from the other database, from other vector databases and a lot of the other databases in general. Since we were thinking about the machine learning pipeline, training and running inference is, you know, has always been a big thing. So we actually just have ready data set notion. So you can do Aperture DB PyTorch data set or Aperture DB TensorFlow data set, where the users then just have to specify filter, and then we can take care of batching and pipelining data. So even if you are going to train with like 1 million videos, you could say split them in batches of 1,000 and fetch 100 at a time per batch. So you can launch that training really, you know, you don't have to wait for the data to be downloaded and prepared. You can just get started, which, you know, oftentimes we don't report the preparation time, but as the data scales, that can be pretty large. And then, of course, we do have a REST API, so you can work with, you know, we have a UI that lets you visualize the images and videos you might have in your data set, but you can also use it with labeling tools, curation tools, so you can just query directly from Aperture. And, you know, we did an integration with Label Studio recently, where you can query from Aperture and then put the labels directly back into Aperture, so someone downstream could query by label. Then, of course, there's all these, you know, if you have to worry about production stuff, authentication, access control, things like that. But really what I wanted to highlight here is the right kind of database can really simplify your overall data pipeline and allow you to focus on data understanding for the organization. And I'm going to switch to the demo real quick, but just wrapping, kind of like putting a wrapper on some of on that recommendation use case I said. Basically, these guys, when they switched over from their concoction of relational database, asset management, scripts, and visualization tools that were separately built to store product metadata, images, embeddings, and annotations in Aperture, if you look at that table, a lot of the things that used to take days or hours go down to minutes of just writing simple queries to one database, which, yay for data science productivity. There's a lot to do already. All right, so should I switch to some examples to see how it might work and hope that the live demo works, because that's always a thing.
Sounds good.
So anyone on the call wants to go try these things out, please go to aperturedata.io. If you go to try free, you can essentially request. Right now we have some preloaded data sets for you to just be able to try. You don't have to worry about setting Aperture DB for yourself with our Docker or any of that stuff. You can just go. We have Coco data set and some YFCC videos. In this example, we have a Celebi face matching example in the second one. And then we have this newest one that we are still iterating on that shows how Aperture DB works with LangChain and how you can build the LLM and RAG queries. So just put your email, you'll get a link in a minute or so, and you can just run those examples from there. But I will jump straight to, let me see an example here. So I thought I would start with just a simple example of how you use Aperture DB with something like LangChain. It just makes it so easy to swap out vector databases that you might use. If you are trying this on your own machine, another thing I would like to mention is you can just go ahead and download or go to our documentation. There's a setup guide, and I'll walk you through how to set up Aperture DB for you to evaluate with your own data on your own machine. So we did all that stuff. What we did in this instance, can you guys see it okay? Make sure.
Yeah, maybe a little bit.
Is it better?
I don't know. Chat, what do you think? Does anyone think this needs to be zoomed in a little bit more? I can see this from my screen, so.
Yeah. Well, that's how much Jupyter Lab zooms it. So hopefully everyone can see it. But these are you can go instantiate. I actually suggest go ahead and try these out. So in this, what we did was, so in the first version, we essentially just took 600,000 paragraphs of Wikipedia data with Cohere embeddings that were available, and we just ingested those. And this, I think Eugene, you've seen this sort of a pipeline so many times when you're asking questions. So we just basically set up LangChain prompt. We chose the embedding scheme. So this was the multilingual model. And for the retriever, we apply the MMR stuff, and then we use Command-R for the LLM that we use to generate the answer. So we define the RAG chain. We also have a non-RAG chain just for comparison. We've ourselves been curious on how do people use all these models? So we've been experimenting. So we have some questions. So let's see how it goes. Very simply, I can say, what's the largest city in France? And it's basically, so for vector search, it's using Aperture DB, and then we implement the MMR computation in our client. So you can see, and we can debate on the quality of the RAG and non-RAG answer. But one of the things that we wanted to see was in the data that didn't have a lot of context about Aperture DB yet, can I ask a question and get something sensible? So, well, we didn't really get answers that we liked. So one of the things we did was to basically crawl Aperture DB, Aperture Data website, and then essentially feed that into the same sort of a question and answer thing, where now if I go here and I say, can I store audio files in Aperture DB, essentially go look for the documentation. And the RAG answer, actually, I kind of like this answer. You can store audio files among other data types because we deal with multimodal data. And it also shows the documentation links. So this, it's just a quick example on how you could just basically use ApertureDB as your vector store and retriever when you're building your building RAG examples. But I want to go and take this a little further. So I have another example, which essentially it still shows. This is not online. This is just my own playground example. So you connect to the database, and here we get into metadata schema. This is where I want to give some examples of the graph. So I'm going to come back to my slides here because as we were talking, data. An important thing to know about data in ApertureDB is that metadata representing all images, videos, annotations, and application information is stored as a property graph. With property graphs, you have nodes, edges. Each of those can have key value properties, and nodes are connected by edges. You can call them entities, relationships, entities, connections, however you want to call them, but essentially nodes and edges in a graph. And then you can group them together. So this class or tag that you see, so this is just like a random application example where I have some freight information, and this freight had some images taken. There were some claims files. This is like an insurance example. And then I can improve on it. As I learn more and more, I can evolve this. The good thing about using graph, and the reason why originally we went with this graph database to represent metadata, was the fact that it's so easy to evolve. You're not tied down into a very fixed schema, which, with machine learning applications, you learn more and more, and you want to enhance that information that you have. So this makes it very easy to evolve it. And because we were able to do memory optimizations, it scaled. It scaled very well, and you got really good response times for our queries. So we were able to basically build a graph database for this sort of scalable use case. And that means now you can evolve this. So for example, let's say you're creating data sets from some of these images. You can indicate that. You can, in fact, go ahead and indicate that some of your models were trained on some specific data set type. And the good thing and the very important thing is this is tied to whatever your application wants it to be. So for example, here, this is a retail example. So in the same graph database on Aperture, I'm able to represent a customer, the stores. They can all have different key value properties. Their edges can have different properties, and you can query and filter on all of these. You can do complex traversals when you want to do graph relationships. You can introduce video clips later on. You can still do the same sort of data set and model as we were doing earlier. So if I go back to this example, this is an example where I went beyond just in the vector indexing some text portion on our website. I essentially created a schema around. I have paragraphs. The paragraphs belong to a document. The paragraphs might be connected to some images, and then I have embeddings for them. And now if I want to search for, let's say this is one of our customers, I want to look for where they appear, I'll basically be able to do vector search to find matching paragraph. And not only that, I can actually say what is the corresponding document that this paragraph is connected to, because if you notice, the document is connected here. And so you are able to find that. You're able to find the images. And if I go look in my result, I'm in the wrong folder. So the documents I was talking about, a download, you could basically access the PDFs. And not only that, you could actually get to the images that are connected to it. So this is where you start going into, when you deal with multimodal data, you want to be able to query and find whatever it is you're looking for. And that's really what this shows. Like, you started out with the vector search, and then you got some of the other data types, and you could do the reverse. You could feed multiple data types in. And for that, what I want to show real quick is we ingested clip embedding. So this, I'm just doing simple vector search. I found, but we ingested clip embeddings. And let me run this. Okay. So if I search for pizza with friends, connected and how to type friends. So what this did, I searched it with text, and because clip maps image and text onto the same space, I was actually able to use text to find images. And from here, I could take any of these images and search for similar images. So that's just some of the, like, how you can deal with multimodal data, how you can use multimodal embeddings in ApertureDB. There is a lot that I could go through, but what I want to suggest is if you guys want, just go and instantiate one of those demos I indicated. We show querying pictures by images by labels. You can see how we query videos. And there are a lot of notebooks that you can deep dive into to see how you can enhance the data as you're querying. So all the things that I mentioned, you'll be able to try in one of our demos. And definitely share feedback if you do end up trying them. We also have a Slack channel to connect. So yeah, that's essentially like, I don't know, Eugene, is there anything else you'd like to see in terms of what you could do with Aperture, or?
I mean, I think this was really cool to see all the different demos. I had a question about the evolving metadata schemes that you were talking about. So one of the challenges with scaling vector databases is you have to hold a lot of vectors in memory. And okay, so I don't particularly understand how graphs work in this case, but like, it seems to me that might be something that you have to do with graph databases as well. Like, so when you add these graphs and these new nodes and things like that, like, is that something like, where is that stored? And like, how does that, like, because you mentioned scalability, like, how does that scale?
Yeah, so okay, that can be a whole talk by itself, by the way, on implementing and building the graph database. And I think I did that once for a CMU database class. But there was a lot of logic that went into, like, what's the fundamental indexing capabilities in the graph. We built it on top of LMDB, which is an in-memory key value store, but then we had to make sure you could persist the data and not lose it, and just provide the general database transaction guarantees. So we have, like, the way we have, I'm trying to figure out what's the best way to answer this question without me going too much into like all the database and caching and everything. That's the harder question, I suppose.
What's stored in the nodes?
So if you look at this example, so for example, there are indexes based on the tag and the key value properties. So you store, you do some optimizations like all the property keys, so like name and role. You basically use them not as strings transferred everywhere. You translate, you use string tables to translate and get into a compressed integer format. Then the strings, you basically use it's basically classically the data structure that you use. So in the graph, we store all these key value properties grouped together by the tags. And then the embeddings have their own index, but there is also a representation in the graph. So we have scaled the database right now to scale to multiple machines. But we have been talking about, like, okay, how do we fetch data from the disk? What gets stored back into the disk? What goes into S3 storage? So that's, I think all of this information. So think about how you would represent tabular data in a relational database, all the indexes you have to build, what goes into the files, and then map that to, like, okay, with graphs, you have to make sure that you inline the edges, for example, because you have to traverse them, and it has to be faster. So the data structures are different, but the concepts are, like, if you build parts of a relational database, you basically start from there, but think in terms of simplifying the traversals, or like making sure you inline things where it makes sense. You choose data set sizes to match with, like, cache line access. And I don't know how else to answer that, sorry.
Maybe we should have you come give like an in-depth talk on, like, the graph side of things. I think this is like a really, like, interesting topic. But I just had like a couple more questions about that before we move on from this. Is like, so does that mean that the vector embeddings are stored in like a different, I don't know, like logical partition than the graph relationships?
Within our implementation, I would say no.
No.
I mean, we do like the backing files for our, so, remember, we also store the data itself, right? So there are things that go in, like, we categorize, put things into different buckets. And then, you have a file representation or an mmap file representation on the disk. And then, so when we start the database, there's a whole process of like, reading from checkpoints, bringing the database instances up. And then there is like, think of the vector indexes in like their own sort of like, file representation of some sort. So you can come from there and rebuild the indexes when you reboot the database. But they are like, they are in the same server, and then they are replicated through object stores for the other replicas. And then there is other, like, if you go, I think on our documentation, there's at least like a quick description of our distributed setup. So here, I mean, this at least shows certain components that go, like, how we use Zookeeper to coordinate some of these things. But yeah, like you said, that's all of these things are going to be like a whole other topic to go deep into.
Yeah. I think I find this like I find that to be like a very interesting topic. But someone has asked the question. Someone from the audience has asked, "How are customers using your product in ways that surprise you?"
Oh, that's a good one. I think very recently it was people trying, like, so annotations can get really out of hand sometimes, and so you have to tie down the formats. And so this was like, oh, can we impose? So one of the things we say about the graph is it's flexible, right? You can evolve it because you need that flexibility as your application evolves. But this particular use case, they wanted to like rigidly tie down. Okay, the annotations can't have any more than these sort of properties. So that was kind of like a surprising thing. The other thing recently that has come up is running this on the edge. So because and on the edge, I don't mean like mobile devices. I mean like when you set up servers, let's say on a factory floor or on a storefront, on the store side. And essentially they wanted to have like multiple Aperture DB instances on each, like per location, and be able to query parts of their, like the local data, do the vector search, filter by metadata, all the capabilities, and then somehow have like a synchronization. Now, actually, I would have expected that they wanted a global synchronization, but that wasn't even the case. That was the part I was surprised about in terms of like, I always pictured there'll be like subset of data at the edge, and then you could do the cloud thing, but they're like, no, we don't need to think up the whole thing. And we have really large scale, and we're not going to have as much memory and storage. So it was like, okay, there were certain surprising aspects of it.
Very cool. How does data governance work inside of Aperture? Like if I have multiple people that need to access the data?
So we do like in terms of like, so multiple people, we support all the atomicity and concurrency guarantees. And so you can, like, if you're reading, writing at the same time, different users, that's just the database transaction that are implemented in the database engine that we have. But in terms of like, in my mind, governance also comes from the fact that, so who access the data? So we have a way of audit logging, who access, what did they access, if people want it, if people want to enable that. But there is also a way of tracking. Like say, for example, you got an original image from somewhere, which was a 4K image that you stored. But for most of your downstream operations, you only needed like, let's say a 500 by 500 pixel version of it. And you transformed it. With the help of the graph, it is possible to track like, okay, this is the entity for the original image, and then this is the new image, and you can connect them. So you can actually track so not only can you enable tracking who did certain operations or added certain entities, but you can track where the original thing came from. So it's possible for you to track that. And while we don't currently have like ready-made calls, you'll have to do some graph operations to do that. But that's something we'd be interested in understanding how people can make use of. Like what we've been asked so far is like, can we go back and see where what the original data looked like? And that's pretty easy to just traverse the edges back to where it came from. And you can, in fact, in the edge itself, indicate what were the transformations that led you to the new type of data.
Yeah, okay. So you can track all the different data and the way that people are using the data.
You have to enable it. And of course, in like, for being able to track that lineage, you would be adding that information as you go along. But that's pretty straightforward to kind of just put it in a layer, like a application logic layer just above using Aperture DB.
Okay. And then one of the things you talked about earlier was like the ACID requirements and stuff like that, the atomicity, consistency stuff. Are there different consistencies for the graph and the vector data?
We do have currently. So the graph, yes, it's right now it's more like a write to one node. So you essentially are updating on one side and then it propagates to the replicas. With descriptors, we have eventual consistency. And if I'm saying this wrong, someone from my team is going to complain about it. But I'll leave it at that. Because at this point, things evolve so fast in the background that I just am like catching up.
Okay. Are there so one of the things that I remember like learning about with Milvus as a distributed system was that there was like different types of consistency that they enforce with the vectors. Do you guys enforce different types of consistency, or is it like we're going to do eventual consistency because our use cases have like shown that nobody really needs anything better than eventual consistency? Or have you run into anybody who's like requested like specifically enforce like read after write or anything like that?
Yeah, no, we actually originally started out with like, we have to do like, we have to be, well, we never really like fully consistent was hard. But as soon as we started distributing, we're like, how strong of the consistency guarantees do we go for? But, as we analyze the workloads and we realize people are okay, like with this sort of workloads, eventual consistency is fine. You of course have to maintain certain like, okay, well, if you delete it in the transaction, you have to make sure it's gone and things like that. And actually the problems get pretty interesting because maybe you started deleting data, but then that transaction rolled back. So our transactions encapsulate not just the metadata, but the data. So we did have to implement some logic in terms of if you had to roll back a delete transaction, you shouldn't lose the images and stuff. But you also can't keep them around forever. And so there was like this balance we had to strike in terms of be able to roll back, but then eventually clean it up.
How do you handle updates in Aperture? So Milvus handled updates by like basically like guaranteeing some sort of consistency, and then Lance. So I talked to Chung a while ago, and Lance does it by like versioning their file format. How do you do it in Aperture?
So we also do like, so when the user does a transaction, they would basically like, there'll be some combination of metadata or image or embeddings like, that you want to add or update. So during that transaction, we make sure that the graph operation succeeds so that we confirm all the data is there, and we can and we change like, the data. We don't necessarily let you update like an image at this time. Most of the times it's metadata about the image that's getting updated. And then you can basically one of the replicas will get the lock on being able to update, and then do checkpoints and propagate it to the rest.
Okay, yeah, I think.
And when we reply to the user, we are certain that the data that we won't lose the user data.
That makes sense, because like when you're working with images and videos, I think it's very rare that you're going to update like the.
Exactly. So we debated on what to do about it, and we're like, okay, well, at least for now, let's it's most of the times metadata, and then if you want to apply operations and create a copy, then you can create a copy. Like what we realize, no one usually wants to lose the original data.
Yeah.
And so you will maintain that information, and therefore you can just basically create the copy for it.
Okay, that makes sense. Okay, so we're coming up on the end of the hour here. There are Just a few minutes left. Audience, chat, do you guys have any more questions?
So I remember, Eugene, you had asked me something about the different, like what we supported in terms of vector search. So yeah, we do support exact and approximate searches. You can choose between different algorithms. HNSW is the one that most of the times people end up using. And then there are different distance metrics. So usually we see HNSW with cosine distances, and you can request the distances as you do the queries. And in terms of like, in terms of like the performance and scale, we, at least in the last measurement that our customers did, were about 2 to 4 times faster at scale compared to pretty popular vector databases, which prompted the customer to switch. And one of the questions, and I think we addressed this earlier, is what if it's not computer vision data but PDFs? We can totally deal with that. You can essentially store blobs in Aperture right now. So even if we don't support exactly the data type you need, like maybe audio, not yet, then you can store it as blob and still get all the metadata and vector search goodness from the database.
Okay. Do you want to call out which vector database they compared against?
I don't know if you want me to.
I mean, I would be interested. I think that'd be pretty interesting. I would like to know. Yes.
I think you know. I told you already. But they don't want us to mention, so I won't.
Okay, that's fine. So I don't know if you know about my history with cosine similarity and how I have been railing against the use of cosine similarity. Do you find that people use other distance metrics as well, or is cosine similarity the most popular distance metric that you see used still?
Well, actually, when we started out working with that customer example I was giving earlier, we only had L2 and Euclidean at the time. They told us to add cosine, but now we see we've seen a mix of L2 and cosine.
No IP. No one's using IP.
Not that I know of, but I'll have to check with my team.
I think inner product is the best distance metric, so that's my.
I'll have to check before I say that. I might be misrepresenting that a little bit, but yeah.
No, I think it's not very common. I don't really see people use it, but it's my favorite one because I think it's like the most computationally efficient. Okay, it doesn't look like anyone's asked any questions in the last minute or so, so I think we can wrap up here. Thank you for coming on this episode and telling us all about Aperture and the graphs and building the graphs on top of the vectors. That's really interesting stuff. I think maybe we'll have to think about having you come on again in a few months to tell us about what's actually going on underneath the surface. I get a lot of requests for the deep dive, so we'll get some feedback. We'll get some feedback from the audience and see what they say. Okay. So one more question. I think we do one more question before we go. How has the architecture changed in the last few years?
Well, so the very first time when we left Intel, we were a single machine database with not much tooling around it. We thought we did a great job building the database, but it was really reference architecture. So ever since, we had to do a lot of evolution. The internals of the database evolved a lot in terms of scalability, reliability. We are now a distributed database. So there was, a lot had to change around supporting distributed transactions. So that basically was the core remained, but a lot had to be introduced. Then we introduced encrypted communication and access control logic. So there was layers that went on top. So what essentially over time, what's remained is the unified API part. You can still talk, it's very similar. It's just become more consistent and simplified. But internally, we had to change the graph engine. We did another version of it. And then we support, some of the libraries went through some changes in terms of how we support visual operations. And then we had to introduce, we started working in different clouds. So there's a layer on the file system side that can talk to S3, it can talk to GCS. So we had to introduce all that. So yeah, it's now the code looks so completely different from when we started out. I did want to leave everyone with some of the things that are coming up. I don't know if the slides are still visible. I just kind of like look out for our LangChain integration and examples. And I'll be in San Francisco for AIQCon. So if people are there, happy to meet. And then Eugene, you've been promoting the Gen AI Zoo. Looking forward to that. And I just wanted to have, let people know, go ahead, request a free trial or try our Docker image. Our documentation is always improving. And on our websites, if you go on our main website, there is a Slack thing. It'll take you to our, you can connect and talk to us there.
Yeah, I'll send out all the links in a post-event email. So you guys will get all the links. Don't worry about getting them now. Awesome. Thank you so much, Vishaka.
Thanks so much.
Thank you so much, everyone, for coming. And I'll see you guys. Well, for some of you, I'll see you tomorrow. All right. Peace.
All right. Thanks a lot. Bye.